Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll learn about binomial expansion, extended. 1 plus x to the power of n will be focus. We'll review binomial expansion which we learned in year 12. We'll consider special cases with radical exponents, look into infinite series and approximation. Let us now connect with what we know to what we want to know. Our approach, engaging minds, help us to perform much better. We can now connect to context, visualize strategy, apply learnings, and bridge the gaps. Engaging minds help in creative thinking and problem solving. Gain the confidence. Get ready for future. We develop both mathematical and social skills. I can be part of your success story. Build strong foundation and ensure bright future. That is the gift of education. You can always contact me on the email address given. Join my classes. Let us now enjoy the class with Amy. Hi, Amy. How are you doing?
Hi, sir. Yeah, I'm good, thank you. How are you?
Very good, very good. So now, today, what do you want to do?
So I was hoping we could go on to a new chapter, still within pure maths. I think it's called binomial expansions. It's kind of touching on year 12 stuff, in terms of Pascal's triangle, the choose stuff as well, and factorial things. But yeah, a little bit of a twist to it, kind of using bigger equations and stuff. So, and timesing things in between x and having like different coefficients of x. So
Okay.
I don't know if that could, change up the way we use binomial expansions.
Sure. So let's see, we are graduating from year 12 to year 13, and now the same chapter on binomial
Right.
theorem will be one step above what we learned, right? So
Yeah,
share with
hopefully
me
not
what
too
have you
hard.
learned, and let's see.
So yeah,
Correct.
expanding 1 plus x to the power of n.
Oh, right. So it's good that they have continued from where we had left last year, right? So let me just see what we have. So, Amy, 4.1, expanding 1 plus x to the power of n. Now, if n is a natural number, you can find the binomial expansion of a plus bx to the power of n using this particular formula. Do you remember the formula? Let us review the binomial expansion a plus b to the power of n. It is written in sigma notation as sigma r equals to 0 to n, ncr a to the power of n minus r times b to the power of r. When you expand, it is a plus b to the power of n equals to nc0 a to the power of n plus nc1 a to the power of n minus 1 b plus nc2 a to the power of n minus 2 b squared, and so on. The numbers of the terms in the expansion a plus b to the power of n is n plus 1. The degree of the polynomial in the expansion is n. The sum of the exponents of each term in a plus b to the power of n is n. Coefficient terms equidistant from beginning and end are always equal. NCR is equals to NC n minus r. All expansions show a decreasing power of a and an increasing power of b. The terms in the expansion a minus b to the power of n are alternately positive and negative. The coefficients are exactly the numbers in the Pascal's triangles. So we had related this to Pascal's triangle earlier. So that is kind of a review on binomial expansion, and now we are going to take a special case where in a plus b to the power of n, a is equal to 1, and we will expand 1 plus x to the power of n. When they have made a as 1, in that case, the equation all of a sudden becomes very simple, right? So we have 1 plus x to the power of n as equal to sum of these terms, where we have NCR and a is 1. So we are only left with the b term, or in this case, the x term, right, to the power of r. Do you see how simple this equation has become now?
Oh,
Where
yeah.
r is from 0 to n all of a sudden, because that multiplier 1 has a to the power of n minus r is now 1 to the power of anything, which is 1.
One.
And
Oh,
that
cool.
gives you a
Yeah.
very simple equation. Is that clear to you?
So yeah, so without like so is this equation that's fully expanded there is exactly what we did last year. It's just the fact that one is basically one, so they just removed it.
Yeah,
Like
this is a
from the
substitution. This is a substitution which you can do no problems, right? You can also substitute x as 1, for example, right?
Oh, okay.
So
Yeah.
if you choose x as 1, then you get 1 plus 1 as 2 to the power of n. So, and you get what? Let us put it. So what do you get? 1 plus 1 to the power of n is equal to the sum of all the coefficients. Do you see that?
And choose R.
So sum of all the coefficients of your binomial expansion is 2 to the power of n. So that is another very important theorem.
Oh.
So 2 to the power of n is actually the coefficients sum in any binomial theorem. Is it okay?
All right.
So
Yeah.
we found that there are n plus 1 terms, correct? And sum of all these coefficients is 2 to the power of n. Clear? So
Yeah.
those good things we have reviewed, which you did last year. Okay, anyway. Now let's get back to this equation. Things become much simpler. As soon as
Yeah.
I put one of the terms as 1, right? So a, we have put 1 in this particular case. Perfect. Now, since a is 1, now look at the expansion. 1 plus x to the power of n now becomes 1 plus nx plus n times n minus 1 factor over 2 factorial. So all these coefficients are much simpler.
Right.
And x is in increasing powers of n, starting with 0. First number is a constant, 1.
Yeah.
So x to the power of 0, x to the power of 1, and last term will be x to the power of n. Is it okay?
Yeah.
So it will go up to x to the power of n, correct? So where the coefficient is going to be 1, correct? Numerator, denominator will cancel
Yeah.
for the coefficients. That is your expansion now. Can you please read this? What is written here? Oh, read from here.
This
Read from here.
if n is a fraction or a negative number, you need to use a different version of the binomial expansion. So is that not that version? It's a different one, or
Yeah,
is it that?
this is a special case when n is a fraction, correct? Because we know that n is a non-negative integer, right?
Yeah, 0 to whatever.
0, correct? But now the same equation has been applied in many different situations. So the whole idea here is that if I have a plus b to the power of n, I can take a common, right? Then I got 1 plus b over a, and everything to the power of n is a clear to you?
Yeah.
Now in this equation, I can take a to the power of n outside the bracket. A to the power of n
Outside.
outside the bracket, correct? Because this is what it is, correct?
Oh yeah.
A to the power of n, and within brackets, I have 1 plus b over a, and this is to the power of n. Do you see that? I have made x as 1, what I was saying.
Oh, yeah.
And the other term is now a fraction. It is the ratio of b over a with the
Right.
It is the ratio of b over a, right? So now that if that is the case, that is in that case, in special cases, and if b over a is actually less than 1, absolute value I should say, because it could be negative also. If it is less than equal to 1, then you could use n as a fraction also in the same expansion.
Oh, okay.
So now again read this.
So if n is a fraction or a negative number, you need to use a different version of the binomial expansion.
Correct.
This form of the binomial expansion can be applied to negative or fractional values of n to obtain an infinite series.
Correct.
The expansion is only valid when the mod of x is less than 1, where n belongs to real numbers.
Correct.
When n is not a natural number, none of the factors in the expression, like n times n minus 1 all the way to n minus r plus 1, are equal to 0.
Yes.
This means that the version of the binomial expansion produces an infinite number of terms.
Correct. Because you're doing n minus r. And when r becomes equal to n, then it is n minus n, which is 0.
0, yeah.
Beyond that, you cannot go further since you have some 0 now, right?
Yeah, yeah.
In this case, since we are now working with fractions, you may not get that 0, right?
Oh, yeah, yeah.
So can you please read this again?
So when n is not a natural number, none of the factors in the expression n times n minus 1 to n minus r plus 1 are equal to 0.
Yes.
So
All
this
these
means,
yeah.
right, so this means that this version of the binomial expansion produces an infinite number of terms.
Correct. Yeah, continue.
You can use a finite number of terms from the binomial expansion to approximate the value of the original expression. So approximations based on the binomial expansion are more accurate when more terms of the expansion are used for values of x closer to 0.
Yes. So another huge application is to find approximate values. And clearly, if I am using 1 over something there in the power, in that case, if my powers are very, very large, that term is approaching 0, right?
Yeah.
And therefore, we can neglect them. So normally we take just first 3 terms or so, and from there we can calculate the approximate value of an expansion. For example, now you can find square root of numbers, cube root of numbers very easily using the first 3 terms of binomial expansion. Is that clear to you?
Yeah, that's pretty cool.
Yes.
Because, like, yeah, so that's just to think of as well. Like, when we were like cubing, you know, let's say 2 plus x when we cube it, even let's say without binomial expansion, there are ways around figuring it out. Like
Yes.
just going, you know, doing our grid method or something and working it out, even though it would take forever, but it still is possible. Whereas if the moment you like cube root something, or that's impossible. Like,
Yeah,
it's not only with this. Yeah.
Correct.
Cool.
So the value of x in this expansion has to be within -1 to +1. We say absolute value of x is less than 1. Is it okay?
Yeah.
Now let's continue with the example. So can we have the first example, please?
So find the first 4 terms in the binomial expansion of 1 over 1 plus x.
Correct.
So first we have to put it in the right form, like we're up here. It was 1 plus
to the power of n. N could be now negative numbers also. Right.
Yeah.
So you have -1 there. So you can now use -1 in your expansion. And so -1, -2, when you take away more numbers, those n factors, right, will be -1. Second term coefficient will be, rather third term, -1, -2, right? And then we have -1, -2, -3. You can continue going like this, right? So the coefficients now are 1, 0, right? And C0, which is 1.
Yeah.
Plus the
nx
minus n, nx. And then n times n minus 1 over 2 factorial.
Yeah.
N times n minus 1 times n minus 3 over 3 factorial.
N minus 3, yeah, 3 factorial.
And then you can just expand them. You know those are the numbers.
Yeah.
And you can take first 3 terms and calculate the value, correct? So you have an expanded series 1 minus x plus x squared minus x cubed plus so on, correct? Simple as that. Very beautiful series.
Mm-hmm. So it says here the expansion 1 plus bx to the power of n, where n is negative or a fraction, is valid for bx, like the mod of bx, sorry, being less than 1, or the mod of x being less than 1 over mod b. Yeah, which is just rearrangement of that.
Right.
Yeah. Cool. Okay. So we got here find the binomial expansion of 1 minus x to a third. So again, similar process, n equals a third. So you just sub it in
Correct.
and solve.
So sometimes the calculation might become slightly more difficult because we are involving a lot of fractions. However, it is much simpler to calculate the value, approximate
Right.
value.
Yeah. Okay. And then
You
it says
have
state
to-
the range.
Yes.
So whenever they say state the range of values of x which is valid, is it always just the mod of x less than 1?
Yeah, because that is the condition. So if
Right.
it is not so, then you cannot apply the formula. Correct? So they have just written x there. However, you should remember that the x value is between -1 and +1. Correct? Otherwise,
Yeah.
you cannot expand it. So I cannot say what is the value of 1 minus, let us say a value which is like 1.1, correct?
Yeah.
But if I say 1 minus 0.5 or 0.7, it is okay, it's valid because
Yeah. It's
that
in
value is
between 1 and -1.
correct. That's what they're ready.
Okay. Yeah.
So similarly for the denominator also, we wrote in the numerator as a negative exponent 1 plus 4x to the power of -2, and now you can expand it with -2 as your n, correct?
So in this case, how come it's mod of x less than a quarter? Because it was 4x.
Yeah. So
And
that
in this
bx,
case, it was x.
yeah, bx has to be less than.
Oh, here, bx less than 1. Oh, okay. Yeah.
So
Cool.
that is how you do it. Is that clear to you?
That's really clear. So I think I can attempt the questions,
Yes.
correct.
Correct.
In
You
this
can take
section.
one of the questions. Yeah. Oh, there are more examples. Good. So can you please read example number 3?
Find the expansion of root 1 minus 2x up to and including the term in x cubed. So yeah, that's all right. And then by substituting in x as 0.01, find the decimal.
Approximation of square root of 2.
Yeah. So they just subbed it in, right?
Right. So the thing here is that
Wait, how come it's not minus a half?
pardon?
Like the mod of x being less than, it says less than a half.
No,
How
because
come the minus 2?
mod is positive, right?
Oh, so it applies to
it
that.
is
Okay.
saying you can write within interval plus and minus 1, and then you can divide by 2, it becomes within interval plus and minus half. Or you can write in mod convention, which is as shown here, correct?
Yeah, yeah.
Let's go through the solution further.
So without further calculation, state how the accuracy of this approximation could be improved.
So how will you improve the approximation? By taking more number of terms, right? Instead of 3, you can have 4 terms, for example, right?
Mm-hmm.
But as now we are seeing, even with the value taken as 0.01, right? So when you had this 0.01 in the formula, 1 minus 2 times this to the power of half, so at this stage, 49 into 2. So I mean, look at this stage.
49
so we have 98
times 2.
over 100, right? We have 98
Yeah.
over 100, which is written as 49 times 2. 49 is 7 square. So 7 has been taken out and square root 2 remains inside. So now we find the value of square root 2 as product of approximate value into 10 divided by 7. Do you see how using this particular formula, they have actually calculated the value of square root 2 accurate to 7 decimal places.
But we were trying to prove, state how the accuracy of this approximation could be improved. Oh, sorry, that's the part C, but part B was. Oh, just substituting in x.
0.01,
Oh,
right. So x value of 0.01, which they substituted, they figured out the value of square root 2. Use more terms. See, instead of 3, you can use more terms, right? Since we approximated by using only 3 terms, correct? Made us calculations simpler. So if you want more accurate result, use 4 or 5, correct?
hmm.
So that is how you can improve the accuracy. Is that clear
But
to
when they went through that, how come they did it like all of that? Can't we just use a calculator and do like square root 98 over 100? Does it not give root 2?
Okay, you already know the value of square root 2, and therefore we are saying it is approximate to 7 decimal places, right?
Oh, okay.
Many times you have to really approximate calculations, which you can use with binomial theorem very easily. That is what they're trying to say.
Oh, okay. Yeah.
Very accurate results. See, we have calculators now, but back then the
There
calculators were
wasn't.
not there. And if I have to find distance between Earth and Sun, how will I do it?
Binomial expansion.
Yes, so the mathematics which was used at that time without calculators was like this, because you have electrical bodies going in different motions and you have to study all
Oh,
those stars.
yeah.
Clearly, all those, calendars made from the lunar calendars which we have
Right. It was through this.
is through this calculation which they
Oh.
did. You get the idea. So they were not
Mm.
using calculators, but they could accurately figure out
So,
so many things, right? In this
wow.
process. So, this 7 digits may for you look, oh, it's very accurate. But no. If I'm talking about millions of miles, no. This is not significant, correct?
Oh, yeah, yeah.
So that is where it comes, and this is the curves, right? So we need to understand how accurately, even by calculations, we can find those values, correct?
Yeah, yeah. Cool. Okay. So
Well,
I'll attempt the rest of the chapter and like using the formula and making sure the mod of x is less than 1 and then
yeah,
applying those restrictions.
perfect.
Hopefully, if I have any issues, I will ask
Sure.
you. But yeah,
The last
thank you,
example
sir.
was pretty good, in which you had square root 2. You see how they manipulated 49 times
Right.
2 is 98, and they got
Yeah.
over 100, right? 0.98.
It's quite hard to see though. Like when I see 98, that's not what I'm thinking. I'm not
Yeah,
going to think
so how do
49
we get
times 2.
square root 2 from here? You get the idea? How do we
Yeah.
get square root 2? And beautifully they turned it out. And that is a very good example, actually. Okay, so
I'll keep
thanks
that in
for
mind.
sharing.
Yeah.
Right?
All right.
Thanks. All the
Thank you
best.
so much, sir. Enjoy the rest of your day.
You too.
I'll see you
Thank you.
soon. All right. Bye.
Here is a very important example for you to try. Show that 1.01 to the power of 1 million is greater than 10,000. That's a very interesting question, which can be solved using what we have learned today. The solution is provided. I would like you to understand the solution and appreciate how we could apply the knowledge learned today.